will be the conclusion of section P.4 on linear modeling. So far, all of the models that we found have been for situations or data that fit a linear equation exactly. Every single point that we had fit on a line. Often the real world is messier than that, and we get data that comes very close or somewhat close to being in the shape of a line, but maybe doesn't quite fit precisely. We can pick 2 points and get an approximate line by hand, but there's a process called linear regression that will give us what's called a line of best fit. It's going to give us the best possible line that comes as close as possible to all of the points at once, rather than just 2 of them. This is a relatively complex mathematical process that's beyond the scope of this course, so we'll always use the calculator when we're trying to find the line of best fit. And the process the calculator uses for this is called regression. In order to practice this, in the example, we're going to look at 2 sets of data. The first one gives us basically the year, and we're going to want to notice that our t-value not be the year itself, but the number of years after 1960, and then the number of all men's colleges during that year. I'd like to start by examining that data to decide whether or not it seems like it's approximately linear. This, by the way, is a very common thing that gets done with years. Years are very large numbers. They're not real convenient to use. So we often pick a starting year and then just measure our t-values from there. I'm going to go ahead and make myself a little column of t-values. 1967 is 7 years after our starting value of 1960. 1975 would be 15 years after. Notice we're really just subtracting 1960 from our year. 1985 would be 25 years. 95 would be 35 years. And by 2012, if I subtract that 1960, I'm going to get 52 years. All right, let's put this data in. We're going to be using the t-value for our first column, and then the n, number of men's colleges, for our second column. We won't actually put the years into the calculator. So we want to go to our Stat menu, and the very first option is Edit, which is what we want to do, put in data. So I'm just going to hit Enter. And I got some old data in here, so I'm just going to go on up to the title of the list and hit Clear, Enter, and the same thing in the first one. Clear, Enter, giving me a blank list to start with. My first column, I'm going to put in my t-values. And in my second column, I'll put in the n values. Looks like we have less and less all men's colleges as time goes on. Makes sense, based on what we know about the real world. I've got my data in here. Let's take a look at it first in a scatter plot and decide if we think that data looks approximately linear. In the y-equals, just check in any equations that you may have put in you want to clear out of there so they don't affect your data. My plot 1 is already turned on. If yours isn't, just go ahead and toggle on up there and hit Enter to turn it on. And then I do want to adjust my window setting. As I look at my t-values, they go from 7 to 52. I'm going to go from 0 to 60. That'll cover the range of t-values that I have. That's a lot of tick marks, so I think I'm going to count by 5s. Men's colleges, 145 down to 4. If I went from 0 to 150, I would see all of those. And maybe a scale of 10 on that one. Again, this is more art than science. You may have slightly different values, but as long as you can see all your points, it's perfectly fine. All right, I've got my window set, so I'm going to hit Graph. And I'm looking at those points, And it does not look like they are really very close to a straight line. They begin to come down here, but I kind of would have to curve over to get to these ending values. So this does not look like good data to find a linear model to me. Let's say data, not nearly linear. Kind of looks like that rather than a straight line. All right, so we're probably done with that one. Let's check on the second table and see if that one does any better for us in terms of linearity. Once again, I've got t-values as the years after 2000. And this time we're looking at the value of the yogurt sales in the United States in billions of dollars for each year. So let's see here. I'm just going to split this column, put in my t-values. After 2000 would be 1, 3, 5, 8, and 10. So these two columns are what I want to put into my calculator. I'll go back to Stat, and I do want to edit again, clearing out my old data, and then entering the new data. If these calculator skills are not second nature to you already, I would encourage you to always kind of pause your video and put stuff into your own calculator so that you get used to it and you'll be able to do it, quickly and easily when it comes to having to do it in class or on a test. All right, back to the y equals. We still didn't put it in any equation. Our plot 1 is turned on, so no problem there. But I probably should adjust my window. Looks like t-values go from 1 to 10 in the table. Maybe I'll go from 0 to 12. Again, I like to leave myself a little room on each side. That's not so much. I can count by ones, and that'll be fine. The N, the number of billions of dollars in sales, is not very big in terms of the numbers here, so maybe I'll just go from 0 to 5. That covers it all, and I'll count by ones. As much as possible, I like to have my data fill my screen because I can better see the shape of the data if I do that. All right, graph, and there it is. Now, I certainly won't argue with anyone who says those points are not all on exactly the same line. They certainly aren't. However, we can see that if we were to draw a line kind of right about through here, although all the points would lie exactly on it, they would all be fairly close to it. So I'm going to say this data is approximately linear, and I can model it using a linear equation. So I'm going to say this data is approximately linear. Although not exactly. Okay, so we're going to go ahead and find the line of best fit using this calculator process of regression. In order to do that, go back into your Stat menu. So far, we've really only used the Edit to put data in. But if you use your arrow key to move over to Calc or Calculate, you get a whole bunch of options. The calculator will do regression for a lot of different types of data. Right now, we're only looking at the linear regression, which is option number 4. So I'm going to select that. And what this is giving me is where my data is stored. Now, I'm going to notice that right now there's actually a mistake in here, and that's actually a good thing, so I want to show you how to fix it. We stored our data in 2 columns that were called L1 and L2. Right now, this says L2 and L2. That's not right. I want my X list to say L1. So in order to do that, on my calculator, I'm going to notice that L1 actually appears right above the number 1 in blue. It's a second function. And so I'm going to go ahead and hit second and then that 1 key. And notice that has changed my X list to L1, which is what I want it to be. Always double check when you start a regression process that your lists are the correct lists where you actually stored your data. For our purposes in this class, the frequency list will always be blank. If you take a statistics course, you may use that. And we're not going to store our equations. We're just going to calculate. And there we go. Rather than mx plus b, the calculator uses the notation ax plus b. So in this case, they're giving us an a, which is really the slope, of about 0.191. Let's use 3 decimal places. And while I'm in here, notice the b value is about 2.089. So I probably should write that equation down. Let's see where I got space right up here. There we go. So from the calculator, I've got my slope of about 0.191 if I round to 3 decimal places, and my y-intercept of 2.089. I will say one more word about this before we go on to the rest of the problem. I've got a couple of other values in here, these things called r and r squared. Those are called the correlation coefficients, and essentially they tell me how good the fit is. The closer the r squared value is to 1, the better the fit. R is going to be close to either positive 1 for a positive slope or negative 1 for a negative slope. In this case, I've got a very good fit. This value is very close to 1, and r squared is still very close to 1. If you didn't get the r and the r squared values, you just need to turn your diagnostics on in your calculator, which you can do in the catalog. I'll show you how to do that real quick in case you want it. Catalog is down here above the 0 key. And so if you go to second catalog, and then go all the way down to the D's, which you can skip to just by hitting the key with the D above it, or just scroll. We've got these options, diagnostic on and diagnostic off. You want diagnostic on, and then just hit enter again, and you'll turn those diagnostics on. If you didn't get the r and the r squared before, go back to stat, calculate, and run your linear regression one more time. My lists are correct now, so I'll just calculate, and you should get all the same values that I did. All right, so this is a pretty good fit. Our data was pretty close to linear. I'm satisfied with my equation. All right. I started down here and I jumped the gun just a little bit. Let's do one more thing first. Let's rewrite this using function notation and the variables in the problem. N is actually our y values. T is actually our x values. So this equation would look like n of t equals 0.191 t plus 2.089. All right. First question, what's the slope of our line of best fit, and what does it represent? We already knew the slope was 0.191. And as far as what it represents, well, what's changing in this problem? It's the value of the yogurt sales over time, with respect to time. So I can say the yogurt sales, I always want to say whether they're increasing or decreasing, and in this case it's a positive slope, so they are increasing. Makes sense based on what I see in the table as well. And they're increasing by that much, 0.191. And that would be in units of billions of dollars per year. Now again, this is a linear regression. It's an approximately exact line, not exact, so it won't be that sales go up by this exact amount every year, but that's about how much they're going to go up every year. I also want to find the n-intercept. N is y, so that's the y-intercept, 2.089, or you can also think of it as plug in the opposite variable, t equal to 0. And I can see that if I do that, if t is 0, I am just going to get the 2.089. This is our starting value at time 0. T equals 0 is just our starting year, the year 2000. So in the year 2000, the yogurt sales, goodness, I didn't spell that very well, were, according to our model, $2.089 billion. One comment here. Again, when we're using linear regression and we don't have exactly linear data, anytime we make a prediction like that, it's always according to the model. That, of course, was probably not the exact value of yogurt sales in that year. It's what our model predicts for us. Rather than writing according to the model every single time, we're just going to kind of make an agreement that when we answer these questions, we're always answering them according to the model. All right, last question about this problem. Find the t-intercept of our line of best fit, and again explain. Once again, to find an intercept, we always set the opposite variable equal to 0. So this time we want to set n equal to 0. If I do that in my equation, I'll have 0 equals 0.191t plus 2.089. And I'd like to solve that for t. So let's see, I got to divide negative 2.089 by 0.191, and I'm getting negative 10.937. And I do apologize. I had that off the screen. Let me go ahead and just run through that one more time real quickly. I was saying it, but you couldn't see it. Again, the t-intercept, the opposite variable, we set n equal to 0. So 0 equals 0.191t plus 2.089. I solved that equation for t and got a result of t equals negative 10.937. All right, so I found the t-intercept, but what does it mean? Well, I have a negative t value. Whether or not that makes sense depends on the particular problem. In this case, t is the number of years after the year 2000, so it would make sense that a negative value would simply represent the years before 2000, and I can probably interpret this. Since it is a year, I'm going to round it to the nearest whole value. I'm going to say t is approximately negative 11. So 11 years before 2000. That's going a ways back. It puts us back to, what, 1989? And our prediction is, in 1989, yogurt sales were how much? N was 0. All right, Definitely according to the model, that is our result. In this case, a lot of you weren't alive probably in 1989, but I go back that far, and I can tell you that although certainly yogurt wasn't as popular as it is today, we did have yogurt. And so I know that that's definitely an incorrect statement. When your model predicts something that is definitely incorrect, we call that model breakdown. And I'd like you to get in the habit of writing that down when you recognize an answer that's not reasonable. Okay, I know there was yogurt sales in 1989, so this is model breakdown. One of the things that you need to get used to is when you are using linear regression or lines of best fit to make predictions, the further away from the actual data in the table that you get, the less likely it is that you're making an accurate prediction. In this problem, I have a fair amount of confidence in this prediction. T equals 0 is only a little bit before my first data point in my table. So I think that that's probably a pretty reasonable prediction for the year 2000. T equals negative 11 is a long ways before the table, and so it's not surprising to me that I got a prediction that's not reasonable. All right, this ends section P.4, and we will start next time with P.5.